Yeah. All right, good morning, everyone. Thanks for joining us this morning on what was a pretty wild weather adventure this morning. My name is Nick. I'm the new head of materials engineering, but I was actually also in the exact same position as you guys because I did my undergraduate degree here at Monash. So we had this branch selection day as well, and I remember all the sort of decision-making process and the questions that you guys might have. So because of that, we can't really cover too much in these slides, but we're going to give you a bit of a flavour, and we've got a couple of students here and a lot of brochures, and feel free to ask a lot of questions afterwards as well. But for those that don't know, I know a lot of you that are doing straight eng certainly have done maybe the first year materials subjects. Some that are doing double degrees may not have any experience yet. But materials engineering is one of the 5 engineering departments here at Monash. Around about 18 academic staff with also some research fellows as well. Relatively small class sizes, about 50 people compared to the other departments, and we're very research active. We're the most research active department. So although there's an emphasis on teaching, there's a lot of research that goes on in the department. So a high number of graduate students, the people that are teaching you are nominally the world experts in the area in which they're teaching you as well. So it's a little bit different to some of the other departments, and hopefully those that have done materials engineering so far in first year have enjoyed it. Okay, so materials science and engineering involves the manipulation of materials and their properties to produce materials that are useful to society and commercially important. So that includes everything that everything is made out of. So, what's inside your mobile phone, why can a plane fly because of what it's built with, why is this roof standing up, and so forth. Okay, so what is materials engineering? To distill it down, for the interests of those that don't know, it's about the selection, processing, and characterization, and also the development of materials, so new materials, next generation materials. So this is a very timely time for next generation materials, as we want things to be lighter, faster, cheaper, stronger. And so it involves creating new, better materials, so new structures, modifying existing materials, okay? So how can you make an aeroplane go faster? You need a different superalloy for the jet, for example, that can make it fly at a higher speed without melting, okay? And underlying all of this is characterization. So I thought I'd put up a picture there. This is an atomic resolution electron microscope image collected here at Monash. And the little dots you see are atoms. So they're atomic columns. The different colors represent different compositions. So this is an aluminium alloy that has some copper and magnesium in it, which is used to make the fuselage and wing skins of aeroplanes. And it has a nanostructure that controls its properties. So as materials engineers, you see these things, and you're really working on the nano-micro level, building up materials. Like, say, for example, a civil engineer may build a bridge with trusses. You're doing that on the micro and the nano level in materials engineering. So there's a sort of a triangle between structure, properties, and processing. We cover all the bases in our department. So we have processing ability, alloy producing ability. We can make polymeric materials. We do 3D printing. We do 3D milling. We look at the structure by various means. And we can also measure the properties. And some of you guys have done this at the very entry level in the first year already. So what do we study in materials engineering? It's really an evolving field. Traditionally it was metals, polymers and ceramics, the 3 core materials that make up everything. Pardon me, but then as things evolve, we looked at composites, and that's a growth area, so hybrid materials, adhesives, rubbers. We also look at fracture, corrosion, nanomaterials and biomaterials. Pardon me. So the purpose of this slide, and a recurring theme in some of these slides, is to show you that we cover the bases and we're across all industries. So a materials engineer is not necessarily going to be employed in the so-called materials industry. They could be employed in the mechanical, civil, chemical, offering support across industries. Pardon me. Okay, so materials science and engineering is certainly booming. So all scientists, engineers, technologists require materials with enhanced properties. So for example, I just thought of 3, this morning that we can relate to. So faster computers. What's the limitation there? So it's not electronics. The speed of electronic conduction is fixed, okay? But it's making materials like silicon wafers that can support higher speed computing. So it's a materials issue. Lighter iPhones, so light alloys. So most of your iPhones, or most phones at the moment, still use aluminium, but it would be lighter if we had magnesium in there. Okay, so there's some challenges there, which can improve our quality of life. And also implants and making them biocompatible. Again, fundamental materials issues. So the materials revolution, changing the way we live. So the range of industries which we employ materials engineers and scientists. Our graduates all get good jobs. I've got some slides about that. But the most important thing that I want to convey to you, if nothing else, is that they work across a whole range of industries. So aerospace, automotive, biomedical, computers, energy, environment, telecommunications, and so forth. Okay, so batteries, it's an energy thing. For batteries to work, you need electrochemistry. Electrochemistry is something we cover in materials. So this is just one example. You know, there's a lot of examples at which you can interrogate the important things in engineering as we move forward. Because you guys, although you're studying engineering now, will be practicing for the next 10, 20, 30, maybe even 50 years. So the top 20 greatest challenges were identified, pardon me, by the National Academy of Engineering in the US. And this is what they list as the top greatest engineering achievements and what some of the challenges are moving forward. If you think about those, there's a whole range of them that are associated with materials. And I thought I'd just hone in on one as some examples, which is high performance materials.